No. Okay, there we go. My name's Ivan Rodriguez. I'm the Director of Technical Events for the INCOSE Canada chapter. Today, we're pleased to have Dr. Alex Ellery join us and give us, I think, what's going to be a very interesting talk called Mining on the Moon, Self-Replicating Machines. Dr. Ellery is a Canada Research Professor at Carleton University, and his specialty is space robotics. Dr. Ellery joined us in Canada 17 years ago when he immigrated from the UK. And first he was at the University of Surrey at the Surrey Space Center, or sorry, that's where he was at Surrey Space Center. I get Surrey confused because we have our own Surrey in
I've
BC.
come across this problem before, yes.
Yeah. Dr. Ellery's education in the UK was he received a BSc with honors in physics from the University of Ulster, Masters of Science in Astronomy from the University of Sussex, and his PhD in astronautics and space engineering from Cranfield. Astronautics, what did I say?
It was near enough.
Close enough. Dr. Ellery also is a graduate of the International Space University summer program. After a few years in industry, Dr. Ellery returned to academia, spent most of his time there engaged in the development of planetary rovers, space manipulators, robotic drills, penetrators, scientific instruments, hence our talk for tonight. In the last 10 years, Dr. Ellery shifted his research into in-situ resource utilization, which sounds very interesting. That's NASA's term for space mining. Dr. Ellery has been exploring an unusual overarching theme of developing the concept of self-replicating machines. He'll explain to us just what that is and what the benefits are, but ultimately it's to industrialize the moon. Dr. Ellery is a director of the Center for Self-Replication Research, or CESER. I'm going to turn it over to you, Alex.
Okay.
If you've got slides to share, you should be able to share them now. And the way we'll do this, Dr. Ellery, maybe I'll let you do the presentation. Let's save the questions till the end. You can put your questions in the chat or wait till the end, and I'll moderate a Q&A session at the end. Now, are you open to, I think it's probably good to give you the flow of not being interrupted. Would you agree?
Yes, that's probably easiest, yes, because I'm sure they'll get interrupted a lot, but yeah.
Yes. Okay.
Can you guys see my screen, my slides? Okay.
We can see your slides and we can hear your voice. So I'm going to mute and let you take it away. Thank you.
Okay, thank you very much. I will be talking about mining the moon, and one potential mechanism for doing so is based on the idea of self-replicating machines. And so I want to talk about this. This has been dominating my research for the past decade or so, and I hope you find it interesting. So this is what I want you to have to bear in mind all the way through the talk. This is an artist's conception of a system on the moon which takes resources that are available on the moon and then converts them into essentially a self-replicating machine. So we have, it's basically an industrial process. So we have, these little rovers that run around, scooping up regolith. Regolith is the term for planetary soil, but without an organic component. And then that is then processed and ground and so on and so forth, and separated into separate minerals, which are then processed to extract metals and non-metals and so on and so forth, and then 3D printed into various components we need for which to build a self-replicating machine. And I'll talk about, how this works a little bit later. But bear in mind that this is the kind of thing we're talking about, and these are basically charging stations and power systems and so on. And again, we'll talk about this aspect a little bit later. So I'll first introduce you to Katvik. This was a micro rover that we built for the Canadian Space Agency. It was 32 kilograms in mass. It was an end-to-end micro rover prototype to demonstrate lunar mining. This is it on field trials at these Canadian Space Agency's Mars Yard. The certain features of it were it's a JCB type prototype. It has a scoop, in other words, for scooping up regolith. It could potentially be fitted with as a loader or a bulldozing blade. It has autonomous navigation capability using something called an unscented Kalman filter, which is implemented on two field programmable gate arrays. It has an exchangeable chassis, which means that you can basically replace this chassis with another type of chassis configuration. And this is an example here. This is an example of something known as the elastic loop mobility system, which is a kind of tracked type of chassis. So this would be useful on highly rugged terrain, the kind of things that we'd expect to see in the polar regions of the moon. A couple of novel features are that the chassis itself, above each wheel station, we incorporated load cells. So this allowed us to measure the loads above each wheel station, and we'll see how we use that information a little in the next slide. It had a hybrid camera mast manipulator arm, so the camera resided on the elbow. This, of course, gives it a very good full observability of the scoop when we're scooping up stuff. And it also had an abseiling capability, and I don't know if I have I don't see a picture of that. It had an abseiling capability, potentially to allow it to descend into sort of like skylights and so on the moon. So this is some of the things that we were doing. We basically one of the methods we wanted to use the rover for was for geotechnical survey. Now, according to Terra Mechanics, we can get an idea of the rover performance by measuring something known as drawbar pull. And this actually involves the interaction of the vehicle wheels with the soil. And from that, we can actually estimate sinkage. And we used a neural net model, which actually enabled us to extract soil cohesion and friction angle estimates as we drive along. And this one here on the left is the cohesion, on the right is the friction angle. And these are fairly fundamental geotechnical data that you would want to have if you want to site things like lunar bases, and also for examining sort of like traversability and so on of terrain. So this enabled us to do this. This is just the chassis by itself undergoing field trials at Petrie Island, which is a small island kind of not far from Ottawa. And basically we use this as a kind of like an emulation of essentially the Martian surface. And the graphs you see there are basically the measurements, that they're basic measurements of load, and also the tilt angles of the pivots that we've mounted the wheels on. We also field tested, well, I say field tested, one of the things we wanted to look at was the idea of like a deep lunar mine, a subsurface lunar mine. And so we wanted to look at the repeatability of the potential fields autonomous navigation system that we'd developed on a test rover. And this shows you that the rover, the student isn't actually controlling the rover is driving itself. He's merely basically he's merely following it, basically with an emergency stop in case something goes terribly wrong. And so we use the potential field technique to allow us to navigate around narrow passages in essence. So, well, where does this leave us? Well, obviously, rovers can be used for surveying, geotechnical survey and otherwise, but also for surveying for minerals. And this is where we get into in situ resource utilization, which is NASA E's for space mining. Now, space mining or extraterrestrial mining and manufacturing impose certain challenges which generally don't occur in terrestrial environments. One is that the energy generation is local, so we have to generate it locally. There's no grid. We can't use manual labor because astronauts are expensive, so we have to do this autonomously. We need to ensure that everything that we put on the moon can be maintained robotically without people. We can't use high weight equipment because that's expensive to put onto the surface of the moon. We also have limited geotechnical data for siting infrastructure. And of course, there are various environmental constraints like vacuum. The dust environment is a terrible environment, actually. We have very wide temperature fluctuations. And there's radiation and micrometeorites as well. And of course, there's a partial gravity on the moon, which is negligible actually on asteroids if we were interested in mining there. Now, most people have been most of the Americans have been focusing on accessing lunar water. There's an estimated average of about 5.6% water ice by mass in these cold traps in the poles. These are permanently shadowed craters. Most interest is focused on the South Pole. Now, the cold traps are about 40 Kelvin, so ice collects in these locations, which are potentially mineable. And in fact, the total inventory of water ice on the moon is estimated about 10 to the 12 kilograms, which is actually quite a small amount. It sounds like a large amount, but it's actually 10 to the minus 4 times the amount of water vapor in the Earth's atmosphere. Now, the rationale for mining water is that it requires minimum processing, but it does require fairly extensive infrastructure. We need to generate solar power. Remember, we're at the poles, so the sun is very low in the sky, and in permanently shadowed craters, obviously, there's no light at all. So the idea is that we have to build these solar farms, which are in place at adjacent peaks of where light is accessible, and then beam solar energy into these dark regions. Now, the beaming distances are quite high, the order of kilometers, both horizontally and vertically. Other problems are, mining operations at 40 Kelvin. We have no idea of how to operate, things like motors and so on and so forth at these temperatures. One idea is to have some kind of like dome-like tent to capture water vapor, which basically where we heat the surface and then capture and then recondense it at passively cold traps. The other idea is we use solar concentrators to sublime the ice, and so on. So you get the idea that actually trying to access this ice is actually going to be quite the challenge. In addition, we have to also implement launch operations. The idea of the water ice, the utility of the water ice is actually being able to split it electrolytically into liquid oxygen, liquid hydrogen, which we can then burn as propellant and oxidizer. That requires cryogenic storage. Well, we're halfway there at 40 Kelvin, but liquid hydrogen requires additional cooling to 20 Kelvin. The other problem, of course, is we can't store it for very long because there's a 3% per day boil-off fraction, which means that if you try and keep it for too long, it'll just boil off. So this means that the propellant production has to be co-located with a launch pad. So we have to build a launch infrastructure again at these 40 Kelvin locations, which is going to be quite the challenge. So why do we want this water? Well, to get the cryogenic propellant, liquid oxygen, liquid hydrogen, it has the highest specific impulse of any kind of chemical rocket. It's also well known in spacecraft engineering. Any spacecraft engineer will tell you that the propellant and oxidizer constitutes the highest mass fraction of all space missions, i.e. the cost. Now, the primary goal for mining water on the moon is to fuel human missions to Mars, staged from the Lunar Gateway, which will some stage in the future, be in highly eccentric polar orbit around the moon. Now, if we look at the Mars Design Reference Architecture version 5, the delta V, that's the amount of propellant we need to get to the moon, to get to Mars from the moon, is about 3 kilometers per second. And this is done in 3 legs. And this shows you here the amount of propellant and oxidizer we need to get to Mars. And it's basically 568 tons required from the Gateway to get to Mars and back. Yeah, and back. So the idea is that but we also need to launch this this propellant oxidizer into the Gateway orbit. And this imposes an additional delta V of 3.7 kilometers per second. And this requires us to launch essentially almost 2,000 tons of liquid oxygen, liquid hydrogen per Mars mission. Now, what we're doing is when we're taking water ice, we're splitting up into oxygen and hydrogen, and then we're burning it. Now, this is not sustainable because as lunar activities grow, so will water demand for other purposes. And we don't want to bring all our bad habits with us from Earth by taking a very scarce resource and then consuming it and burning it. So one option rather than that is to focus on the oxygen. So we supply the hydrogen from Earth, but the oxygen can be extracted from minerals rather than water. And in fact, if you look at the mass ratio between liquid hydrogen and liquid oxygen, the mass ratio is 6:1. So we require almost 500 tons of oxygen, but only about 80 tons of hydrogens, which we can bring from Earth. So we can get the lion's share of the cost saving by mining minerals rather than water. And the minerals, of course, are highly plentiful. We can also use renewable energy sources for launch. Rather than consuming propellant, we could potentially use electromagnetic launchers, which would save us 1,300 tons of fuel. So there are approaches that we can utilize when we go to the moon, where we can attempt to impose sustainability. It does mean it's more challenging to do this, but I think it's the right way to go. In addition, in the future, we're going to need water on the moon. Human consumes about 4.5 kilograms of water per day. 6 kilograms per day, and this amounts to about 40 tons of essentially water per year. The current methods of closed-loop ecological life support systems offer fairly high recyclability of water and oxygen. It's about 80% for water and about 95%, I think, for oxygen. We also want water for regenerative fuel cells. We'll also need water for lunar agriculture. The soil is toxic. So any kind of agriculture we want to support humans on the moon will have to be done through hydroponics. And so this means water. But this water can be recycled. We'll also need water for industrial fluids, things like lubrication, machine coolant, drilling muds, and so on. So I do believe that we should be, if we are going to try and take advantage of the moon's as a source of propellant, we should be focusing on the oxygen and not on the hydrogen and on the water. So let's take a step back and look at the mineralogy of the moon. The moon has a range of resources from volatiles, the regolith and minerals, and so on and so forth. But there are several constraints on the moon. It's deficient in certain elements, most notably copper, sodium, and halogens. And indeed, zinc, tin, and lead are also deficient. So this has impacts for things like solders and brazing alloys. In addition, there's very little organic material, so we can't utilize plastics on the moon because we can't manufacture them from local resources. So these constraints define gaps where we can perhaps make substitutions. So, for example, instead of copper, which we use as an electrical conductor, we can use aluminium, for example. And we can exploit material multifunctionality, which I'll show you in a few moments. For example, aluminium basically is a multifunctional material that can be adapted for many different applications. will require some reagents to be brought from Earth because of the lack of halogens and sodium. So we're proposing that we bring salt with us to the moon, which we use as a source of reagents, but these are not consumed, these are actually recycled, and we'll see that in a few minutes. I'm also suggesting that maybe there are limits as to what we want to extract from the moon. Chromium and manganese are quite often used as alloying elements. It would be very challenging to actually extract these two, but we don't need them because chromium is actually primarily used to add corrosion resistance against a wet oxidative environment. This doesn't occur on the moon, although it does occur on Earth, it doesn't occur on the moon. And of course, we can both dispense. What we tend to do in alloys, we tend to trade manganese against carbon for malleability and for hardening. So we can eliminate both and adjust our designs accordingly to cope with the malleability of purer metals. So in general, although in terrestrial alloys we tend to fine-tune material additives to optimize physical properties, and quite often to reduce processing temperatures, this is not an issue that we have on the moon, because as we'll see later, actually energy is actually something that we have a reasonable amount of. So the lunar geology is relatively simple. It has a few common rock-forming minerals: plagioclase, feldspar, and particular northite, which we'll look at in a moment. Pyroxene, olivine, ilmenite. And these are the main minerals. And so what we've done, we've created this demandite concept where we map functional material requirements with the available resources on the moon. And in fact, about 10 basic materials can supply the full functionality of all subsystems required of a generalized robotic spacecraft. And again, we only require a minimal set of reagents, some kind of, something that is the carbon, nitrogen, and sulfur, which we can recycle, and we import salt from the Earth. So this is the demandite. On the left-hand side, you'll see the functionality that we need to employ with different materials. The numbers actually are the approximate allocation for a generalized spacecraft. Where I've put a plus sign here, this is basically an adjustment beyond 100% to look at specific things. Like, for example, a lunar base, we will have compressive structures, but in most spacecraft, you don't have compressive structures. And in addition here, I've also added 250% for fuel on the assumption that we're using hydrogen oxygen. So let's take a look here. So for example, electrically conducting wire, that's about 7% roughly of a spacecraft's mass. We can use aluminium, we can use Furnico, such as Covar, for high temperatures, and we could also potentially use nickel. If we look at electrical insulation, we can use things like glass fiber, we can use ceramics of various kinds, we potentially can use silicone plastics, but I've pretty much discarded that more recently. The advantage of silicone plastics is that the backbone is not made of carbon, it's only the side chains which are basically carbon, so that minimizes the amount of carbon consumption. So what we have to do is we have to start processing this material. So obviously, the more processing you do upstream, the more energy you save downstream. So the earliest parts of physical processing are quite crucial. So we've been doing things like ball milling experiments. This is our ball mill here in my lab, and we've been grinding the regolith particles into using balls into kind of like essentially single mineral particles, and that's what you see here. This is the result, and this is basically an electron. This is like a microscope image of the individual particles that we've ground. So this is actually essential for preparing material for subsequent processing for downstream processing. So the first process we want to look at is if we want to take one of the four minerals I mentioned was ilmenite. Now, if you heat that in the presence of hydrogen at 1,000 degrees, what will happen is you'll end up with iron metal, rutile, which is titanium oxide, and water, and then you can split that water electrolytically to recycle the hydrogen and recover the oxygen, and the oxygen can be used for breathing and so on and so forth. What we're interested in here is the iron in particular, and this can be separated by liquation at about 1,600 degrees. And if we can add just a few more materials, we can get a range of different alloys for use on the moon. So, for example, we can add, let's say here, we'll try and minimize the amount of carbon we use, but essentially we can have cast iron with a bit of silicon, tool steels, but we could substitute for that with silicon, which we'll look at later. We can create Inovco, silicon steel, Covar, cryogenic Fernico, permalloy. So we're starting to build up with access to a certain limited number of materials. We can start to build up an array of alloys for different applications. Now, one of the things we're going to need are materials that don't really occur indigenously on the moon, but they have been deposited on the moon by meteorites. And so this is where we can actually get access to things like tungsten, nickel, and cobalt. So we know that theoretically we expect about 25% of lunar impact material to survive on the surface or near the surface of certain large craters. These are the very large craters. So some of these craters appear to have what they call mass concentration signatures, which may indicate the location of nickel iron meteorite material. We're not sure. There are a couple of theories about what is underneath these craters. One is like mantle rebound, but the other possibility is nickel iron material. So the typical nickel iron material you get delivered by meteorites is dominated by camosite or tynite. This is a variable mix of iron and nickel alloys, and they typically have about 0.5% contamination with cobalt, which is also a useful material. And if we can access this material, it means that we could start to build some special alloys, such as things like alnico, which is the basis of very, very strong permanent magnets. So when we're at Carleton, we decided to try and search for or emulate whether we could find nickel iron material using magnetic surveying. And so we fitted our CatVic rover with a boom-mounted magnetometer and basically ran a magnetic survey of campus. And what we did detect was actually an underground storm sewer and a local fault. So we actually demonstrated we can use magnetometry to potentially search for magnetic signatures. We've also been, once we've located these asteroidal materials, they're likely to be underground. So this means we're going to have to drill. So we've been working on drills for a number of years. In fact, this is a drill here that we built for McGill University for ice coring for their astrobiology people. And since then, we've also been looking at bio-inspired drilling based on the ovipositor of the wood wasp, which you see here. This basically has a series of cutting teeth and also a series of pockets for excavating in the hole. What the wood wasp does, its ovipositor basically drills into the bark of trees to lay its eggs. This is the principle of it. It basically is two valves essentially which reciprocate against each other. The advantage of this particular approach is that it doesn't require, once it's gained purchase into the borehole, the start of the borehole, it no longer requires any weight on bit, which basically minimizes the structural loading on the drill string. And so this has an advantage. For example, if you want to drill into under very low gravities. It can also be coiled for compact storage, much like a steel tape can be coiled. And so we've been looking at mechanisms to do this. And so we don't need to have these very, very long drill strings. We can basically coil them up into a compact structure and then deploy them as needed. So this is something we were working on for a while, but we haven't been able to continue that work because CSA have not really been terribly interested. So once we've extracted this nickel iron from the subsurface, we then need to separate it. And in fact, there is a technique called the carbonyl process, which is extremely dangerous, by the way, because it basically converts metal into vapor, which potentially you could breathe, which would be disastrous. And once it's in vapor form, in the carbonyl form, we can fractionally distill it and then decompose and then purify it back into its metal. We do need a catalyst for this, sulfur, but we can recover sulfur from troilite. Troilite, fortunately, is basically occurs in meteoritic inclusions that we get with M-type asteroid material, so it's already there with the metal, and so we can extract this quite readily to end up with sulfur. So looking at another mineral, an orthite in this case, this is a very common highland mineral, and we've actually employed HCl leaching, which is essentially an artificial weathering process, and we've done this in the lab. We've actually managed to precipitate silica here, and we've also managed to basically extract alumina. We can also, what we've got here, we've taken this anorthite here, and we've used HCl and a little bit of water to essentially extract everything out of it. So we're utilizing almost 100% of this mineral. Calcium chloride is also useful because we will need that for the next step. We can also apply a similar treatment with HCl on lunar orthoclase to create kaolinite clays. And kaolinite is the basis of porcelain. So we can start to build up a range of different ceramic materials as well. Ceramics are, most people, when we talk about mining the moon, we tend to focus on the metals, but the ceramics are also very useful. Alumina, for example, has physical properties second only to diamond. Silica, of course, is used also in refractory ceramics for thermal applications. We can also use ceramics for tooling and various other applications, and we potentially can manufacture cermet to provide a material with high strength and high temperature tolerance. One of the difficulties with that we'll talk about later when we talk about 3D printing is that typically when we process ceramics, we tend to do it within a polymer binder. This is not viable on the moon because we can't manufacture polymer in any quantity because there's so little carbon. But potentially one of the things we will be looking at is trying to process ceramics directly thermally using Fresnel lenses, and we'll have a look at that in a few minutes. So this actually points us towards we can also create glasses because of silica. We can actually from silica we can generate fused silica glass, which is also transparent. It's optically pure, and it has very, very fine qualities. We can potentially manufacture Fresnel lenses, and we may even be able to manufacture things like optical fibers at some time in the future. But we're starting to build out, particularly from porcelain. Many of you, I live in an old house which was built in 1912, and one of the problems with these old houses, they quite often still have knob and tube technology. But knob and tube technology, although it's not desirable now in houses. It's still a functional way of doing electrics. So potentially we can do things like electrical insulation and so on. We could adapt knob and tube technology for lunar bases on the moon. So this is our lunar industrial ecology. Now, I realize this is a very busy slide and that it's kind of like a bit overwhelming, but we've already discussed lunar ilmenite. We've also already discussed nickel iron meteorite processing, and we've already discussed lunar anorthite. But there are other materials we can extract. For example, from olivine, we can extract magnesium. We can also recycle lunar volatiles, carbon, nitrogen, sulfur, and of course salt we can get from the Earth. So the idea is that our lunar industrial ecology yields us a set of metal oxides. So what do we do with the metal oxides? We need to reduce them to get metals as well. And we have we've already demonstrated this now since I wrote this slide deck. We have we have taken a technique called the FFC processes, which is called molten salt electrolysis, where we've reduced, it can reduce any metal oxide to greater than 99% purity. It's very energy efficient. It requires only relatively low temperatures, about 1,000 degrees or so. The material undergoes a solid state reaction, so the oxides and so on are not molten. The only thing that's molten is the salt. And basically oxygen is evolved at inert anodes, which can then be stored for human processing. So basically, it takes something like the alumina and strips out all the oxygen out of it, and so we end up with aluminium metal. And we've actually performed this experiment in our labs just this year. This is an example of the technique applied to rutile. This is basically titanium oxide powder. This is the end result with the titanium powder after the process. And in addition, this potentially could be 3D printed directly in metal form. And in fact, we're also doing that ourselves with our own setup, where we've extracted molten aluminium, and we've also created rods, and then which we've drawn into wire feedstock for 3D printing using electron beam additive manufacturing, which we're doing with NRC. So assuming that we've got rutile, we've reduced it to metal, we can start to create titanium alloys as well. So we have aluminium, we have titanium. We don't use vanadium. Vanadium is commonly emitted in medical applications anyway because it's toxic. So we can create things. We can also create with titanium. We have nickel. We can create nitinol, which is a shape memory alloy. We've done experiments with this, as you see here. We've done various experiments for solar sail applications. But one of the things we played around with was to try and create a shape memory alloy linear actuator to act as an artificial muscle. Now, one of the things you'll notice here is that the wires are very, very long. This is because the strain in it is only about 5%, so you're getting an extremely short stroke. And this illustrates one of the issues you have with smart materials is you can either get good torque output or you can get good stroke, and you can't get the two together usually. So going back to aluminium, now aluminium is a multifunctional metal. It can be used as a thermal conductor, a thermal radiator. It's an electrical conductor. It's a lightweight structural material. It can also be used as a welding material, as in the thermite. We can start to build out a set of aluminium alloys. So aluminium 1000 we've been working with 3D printing. We've actually also created a version of 6061, which we've omitted the copper and the chromium that's normally in it. And we're currently characterizing the 6061 aluminium, the lunar version of aluminium alloy that we've created. And Alnico, of course, is a fantastically useful material for permanent magnets. And we'll see why this is significant a little bit later. So we've been working with NRC. This is the NRC setup. This is their EBAM facility, electron beam additive manufacturing, and we're basically building. We're currently building an aluminium structure to represent tankage that we could potentially do on the moon. I'm not going to mention any more about that because I'm aware a bit of time. We're also creating our own multi-material 3D printer based on Fresnel lenses, and I'll just see if these videos will run all together. So we've created our 3D printer, which is on the right. We're still in the process of building it. The idea behind our multi-material 3D printer is to use a Fresnel lens as a solar furnace to melt aluminium alloy. We've already demonstrated that actually we can melt aluminium alloy and deposit it onto silicone plastic insulation. And so what we're trying to do is create this multi-material 3D printer, which has multiple heads. So we have a fiber optic head, and we have a silicone plastic extrusion head. This is the silicone plastic extrusion head here. And with the Fresnel lens, we can basically melt aluminium and 3D print it. And there are various phases we want to go through to widen its applicability to steels as well. But we've come across a slight problem in that focusing the hotspot through fiber optics is quite the challenge, and we're currently scratching our heads about that. So this brings us to self-replication. Well, I believe that self-replication is the only robust way to do space exploration. What it offers us is the idea of exponential growth in productive capacity. So what we do is we launch a single 10-ton self-replicating factory to the moon at, say, a cost of $7.5 billion. Now, if we crunch the numbers using this formula here, let's say 2 offspring per generation. In 13 generations, we have 1.5 million of these units. That's within 13 generations. That's a phenomenal number. So our initial capital cost of $7.5 billion is now amortized over this exponentially increasing productive capacity. And so the specific cost has dropped to about 50 cents per kilogram of productive capacity. So now, if each 10-ton factory takes 6 months to build, we have 1.5 million factories in just 6.5 years. That's a phenomenal ability to industrialize the moon. So I think it's crucial that we try to develop this technology, because the sheer attraction of it, it will transform the way we do space exploration, because self-replication actually effectively sidesteps launch costs. So there are certain constraints we need to observe when we're looking at self-replication, and the most important constraints are associated with closure. So we need to have material and parts closure. So if you look at a mobile phone, for example, you have a whole set of components which come from all over the world. They've been mined from all over the world. They've been manufactured and so on and so forth and processed. And it has a huge fan in to your mobile phone. What we need to do to close the matter loop, you have to narrow that fan in as much as possible so we can close that self-replication loop. So we want to do that. We want to restrict the raw materials inventory to minimize mining and chemical processing. And we're already doing that essentially with our demand list and our industrial ecology and using the FFC process. We also want to restrict our parts inventory to minimize manufacturing and assembly costs. Now, I'll come back to that in a few minutes. So another aspect is energy closure. Now, most people who work in the energy industry understand this quite well through the concept of energy return on investment. So we need to ensure that the energy required to create the self-replicator is less than the energy required to the amount of energy that needs to be generated. So to close the energy loop, we want to make maximum use of direct environmental energy, such as thermal energy. We want to maximize the electrical energy conversion efficiency, and there is a technique called photon enhanced thermionic emission, which promises conversion efficiencies exceeding 30%, possibly as high as 50%. We want to minimize the energy wasted in processing a waste by eliminating waste entirely. And this is where our industrial ecology comes in. And we want to minimize energy consumption by restricting physical processes. So 3D printing, basically with 3D printing, you minimize energy wastage because you're not generating, unlike subtractive processing. We also want to impose information closure. This is another interesting area. So to do that, we want to maximize parts reuse. In biology, this is called exaptation. So what this does, it minimizes the amount of energy we need to specify a particular device. So for example, we could co-opt electric motors to store energy as flywheels, and vacuum tubes, which we might use for computing, can be co-opted for energy conversion, i.e. thermionic emission. And I'm looking for a PhD student to actually start working on looking at CAD, the way in which we use 3D prints from CAD. At the moment, we do it through slicing a solid model, which is very information dense. So what I want to do is to analyze, see whether we can grow these, represent essentially 3D structures as growth algorithms, which would reduce the amount of information we need to store object coordinates. So what is a self-replicator? Well, John von Neumann stated quite clearly that, well, that a sufficient but not necessary condition for self-replication is something known as universal construction. So a universal constructor is a kinematic machine that can manufacture any other machine, including a copy of itself, given the appropriate resources. So we have matter, energy, and information. And in fact, this concept is a generalization of the universal Turing machine. So we can idealize this, as you can see, this is a NASA image here, as a kinematic arm, which is basically manipulating a sea of parts. No, Rachel, you can't come in here. No, you cannot. No, go. Sorry about that. So we can adapt this universal constructor. Hang on a second. Bear with me a minute.
While we're waiting, if anybody has any questions that you'd like to add to the chat, please go ahead. Otherwise, hold on to your questions, and we can take turns asking Alex when he gets back, or when he's done the presentation. Thank you.
Hi, sorry about that. My son came in and wanted to sit in, but I had to shiver him out. Anyway, how am I doing for time?
We're getting close on time. Now this session we did say was going to take a bit longer than some of our other sessions.
Good. Okay.
But how much longer do you think you have?
Maybe about 10 or 15 minutes.
Okay. Good.
I'll try and speed it up.
Okay. Yep. Please proceed.
Okay. So we can adapt this kind of idealized concept to an unstructured environment by employing a suite of kinematic machines. So we have load haul dumpers, drills as mining robots, any kind of mills, lathes, 3D printers, manipulators, and so on. And so what these machines all are, they are all kinematic machines with specific kinematic configurations of electric motors. So if you look at a lathe, that's a configuration of electric motors in one configuration. A mill, CNC machine has kinematic motors in a different configuration. So basically, we're talking about essentially all these machines are kinematic machines or robotic machines, and the core of any kind of kinematic machine is going to be the motors, the computational electronics, and the sensors. And this illustrates here. The idea is that if we can manufacture things like our motors, our electronics, and our structures and so on, these all feed back into the systems that have created them. And this is what we mean by a self-replicating machine. Why is that not working? So the idea is that this 3D printing suite and also various other types of kinematic machine to collectively constitute a universal constructor. And the core is basically the kinematic machine. The motor, all machines in production are essentially kinematic machines, and any kinematic machine is a specific configuration of motors. And so this is why we're focused on the components, the mechatronic components of kinematic machines. Now, one of the first steps towards, which actually inspired me quite a number of years ago, was the RepRap 3D printer. Now, it can print many of its own plastic parts, particularly the white bits were printed by its daddy. And to convert that into a full self-replicating machine, we need to deal with obviously the metals, we need to deal with the joinery, and in particular, we need to 3D print the electric motors, the electronics, and the computer hardware software. In addition, we have to have a self-assembly, and so this is a proxy for manipulated motors, and we also have to supply an energy source as well. Now, we also have to process materials into the feedstock for the 3D printer, and this is what we've been discussing with ISRU. And so from the 3D printed electric motor and electronics, all else follows. So we've actually been doing experiments in trying to 3D print electric motors, and we've been through various configurations. I'll just show you. This is one where this is basically a purely this was a dual excitation motor, which was made out of soft magnets. We basically used this material called protopasta, which was 50% iron powder in a 50% PLA matrix. We started to get better, so we got from Oak Ridge National Laboratory these 3D printed permanent magnets, and this enabled us to do some start to 3D print more of the motors. Now, the biggest challenge we had was actually doing the wiring. We started off with pancake motors. We used a number of different approaches, from photolithography to utilizing this copper-based material for extruding this copper-based material. Of course, it melted for the high voltages we need for motors. And we ended up using a technique called laminated object manufacturing, as you see here, which is basically to create a copper sheet and then etch it with a laser and then pull away the unwanted components. And so this was the pancake motor, this pancake motor here running. And so that appeared to work quite well. But pancake motors are not ideal because they're very low torque. So what we did was we wanted to create a generalized DC motor, and we did. This is what we created. So again, the difficulty was with the wiring. As you can see here, it's fairly thick. Unfortunately, you can't make it into very thin wire if you're going to wrap it transversely like this. But this we had to do manually. But nevertheless, we were successful in building a fully 3D printed electric motor here. So we had basically soft magnets, we had hard magnets from Oak Ridge. We're currently developing this further as I speak. I have a student working on this, developing this a little bit further in conjunction with the University of Waterloo. So we've demonstrated we can 3D print an electric motor, at least in principle. So what about sensors? Well, we can potentially create sensors as well for tactility. The simplest piezoelectric material is quartz, and as we saw earlier, we've actually extracted silica from alumina, though we haven't actually converted into quartz. That takes high pressure and basically melting with sodium carbonate, and then you crystallize the quartz hydrothermically. We haven't done that experiment yet. But potentially, once we have quartz, we can do all kinds of interesting things with it. We can do things like fairly accurate mass measurements in a quartz microbalance. It also provides the basis for tactility, for pressure sensors. And this at least it provides us with the potential for creating like tactile sensing in robotic machines. We've also been looking at how to create a camera. Now, I focused initially on selenium, and this is found in association with in carbonaceous meteorites in the conjunction with sulfur. And so we can extract this quite readily. We haven't demonstrated this. That's mainly because we've kind of discarded this notion. And one of the things we're looking at now, working with an Estonian university, is using troilite essentially as a photosensitive material, and this is going to be much easier than finding selenium because of the sort of like the very low ratio of selenium to sulfur. There's a lot more sulfur in asteroidal material than there is selenium. So we're currently looking at that at the moment with an Estonian university. So once we have this solid state material, once we have our photosensitive material, then we can potentially create a photomultiplier tube. And basically, this is the structure of a photomultiplier tube. We can use our photosensitive component on the photocathode, and the rest of it basically are electron amplifiers. These basically can be the coatings here can be alumina and or magnesium oxide. So we have the raw materials that we need to manufacture essentially photomultiplier tubes, which can be arrayed to form a kind of like a coarse resolution camera. Now, given the coarse resolution, there are various techniques we can do to exploit this coarse resolution, and one is to be able to use the motors. We can use active vision by shifting gaze across the visual field, where we can overcome the limited resolution that we expect from a photomultiplier tube-based array. And we've actually been looking at using techniques called forward modeling, which emulate the human cerebellum on trying to control the camera motion to minimize the error of where we're pointing at in the visual world. So what about electronics? Well, we can't use solid state electronics on the moon because we don't have the materials and the sophistication there. But potentially we can go steampunk, and we can use vacuum tubes, and these are thermionic devices. Tungsten we can access, the coatings we can access, nickel we can access, cobalt and silica we can all access. So potentially we can manufacture vacuum tubes from lunar sources. So we haven't actually done that. What we have been doing is looking at different architectures. Now, if we try to build a CPU out of vacuum tubes, it'd be the size of a block of flats. So what we've been doing is we've been looking at alternative architectures, and in particular what we've been looking at are neural net architectures. And we've been building analog neural net circuits to implement very simple behaviors in a simple rover, just to demonstrate the principle of using neural net analog circuitry as our computing medium in essence. And this is actually just using two neurons. This little rover basically is the charging cycle, the discharge cycle that's causing it to jerk. But the actual principle of obstacle avoidance was demonstrated just using two neurons. Beyond that, as well as neurons, we've actually also been looking at implementing the back propagation algorithm in circuitry, and we successfully did this as well. This is basically two boards. This is the forward board through the neural net, and this is the back propagation board, which basically allows us to change the weights of our neural network. And we've done this actually in hardware. And this rover was trained a very simple function to stop at an obstacle. Although that seems very, very simple, I think it's the first time this has been shown to actually implement a back propagation algorithm in a circuit. So this means we can update the weights in our circuit, in our neural net circuit, but unfortunately not the topology, which actually potentially is an advantage because it imposes a limit on what the neural nets can learn. This potentially is actually a useful way of stopping the self-replication process if necessary. Okay, I'm going to skip over the thermionics. Basically, I've already mentioned that we can use thermionics for energy conversion. There is a technique called photon enhanced thermionic conversion, which potentially gives us 30 to 50% conversion efficiency. We also can use flywheels, which are motors with, kind of with a rim, to store energy over long periods. And potentially we can get 100 watt-hours per kilogram specific energy storage using glass for the rims. So why self-replicating machines? Well, I think to industrialize the moon, why would we want to do that? I think it's very important for us to do that because I believe that we are setting ourselves up for a disaster in the near future when it comes to when we look at fossil fuels and terrestrial renewables on Earth. One of the things I'm interested in is solar power satellites or space-based solar power. And if you look at space-based solar power, you can start to see why it becomes attractive because it has many of the similar properties as fossil fuels, but not many of the disadvantages of terrestrial renewables. And in particular, if you look at the power density of renewables, they are potentially will be competing with other uses of other land uses. Whereas with a solar power satellites, you can get orders of magnitude greater power density than you can with terrestrial renewables. And this means that there will be less competition for land use. So just to cut a long story short, if we tried to launch, if we tried to provide our energy needs using space-based solar power, we'd need a huge constellation forming a geostationary ring around Earth. It would provide energy for 24 hours a day, 365 days a year. But the cost would be $75 trillion, which is enormous. So that's not feasible. So the only way to do it, to build such a huge fleet of solar power satellites, is to build them using resources that are already in space, i.e. on the moon and in asteroids. So that's my talk. I'm convinced that that sooner or later with terrestrial renewables, we're going to end up with limits and constraints. And the only way really to get 100% renewable energy on Earth is to generate it from space and beam it down. I'll leave it there. Thank you.
Excellent. Thank you very much, Dr. Ellery. That was a very interesting talk. We don't have a ton of time left, and we have lost a few of the participants, unfortunately. But just one question, and we'll open it up if others have questions. But I'm struggling a little bit with the whole energy equation here and conservation of energy. I see for a lot of this processing, we need, I saw figures of 1100, 1300 degrees. I think there was one upwards of 32 or 3300 degrees.
Yep.
Now, what's the overall energy equation here for what it will take to do the processing versus what we get as a byproduct?
The short answer is I don't know yet, because we're not sufficiently developed to actually come up with any reasonable numbers.
Okay.
But the principle is obviously we need to be able to, for example, for the processing, for thermal processing is actually relatively straightforward because we can use thermal energy directly, Fresnel lenses, for example. So we don't need to convert that into electrical energy.
Okay, right.
Similarly with things like, for example, like a magnetron, for example, potentially you could heat the cathode thermally directly without converting into electricity first, and therefore you lose a stage, a conversion stage. So there are ways and means if we can exploit thermal energy directly where we need it, and basically use electrical energy where we need that.
Okay, so there may be some opportunities. All right, Peter, I see you went to video. Do you have a question?
I do. Thanks for your talk, Alex. It's been a while since I heard you chat. There are a lot of technologies that you went through here. I would say it's almost like pushing a snowbank one snowflake at a time because there's so many technologies and fundamental material science principles that need to be kind of revisited for application on the moon. My question is, what do you think is the first application? Is it like a refueling station? Is it to generate oxygen for a human habitat on the moon? What do you think is the first application that this could be applied to?
Well, that's an excellent question. I think it'd probably be supporting things like a lunar base or a set of lunar bases. The Europeans have got this concept called the moon village, where different people, different actors will have different bases and they'll collaborate, communicate, and operate independently and so on. One of the problems I have as a space engineer is how do we make space exploration relevant to ordinary people? Having astronauts playing around on the moon doesn't, there are sound arguments saying we shouldn't do that because we have other earthly issues and problems to deal with. My view is that we need, in order to make space exploration relevant to everybody here on Earth, the solar power satellite to me is a sound reason to make this kind of thing absolutely relevant for individual people. I actually think we, as a species, we've already outgrown our planet's capacity to support us in the lifestyle to which we all aspire, which continually grows without limit. And the only way in which we're not going to like soil our own planet is to bring energy in from outside, essentially exploiting lunar resources to build these solar power satellite fleets.
Okay. So you're thinking manufacturing of the solar panels, etc., large kind of arrays to be able to then power our needs as we move to the future, maybe one of the first applications.
I would hope, well, it may not be the first application, but certainly I think that's the most compelling application.
Okay.
Yeah. Thank you.
Does anybody else have any questions? Free to unmute. Anybody has any questions? Going once, going twice. Okay.
Well,
I think we'll. Oh, did we have somebody?
yes, absolutely.
Yeah,
and
go ahead, Josh.
if no one else will, I'll absolutely jump in.
Yeah, please.
So this is an absolutely fascinating topic and coverage of that topic. It reminds me a little bit of the saying, to make an apple pie from scratch, first invent the universe.
Yes. Yeah.
And that once you've got the sort of general purpose machines you've described, you've got a general purpose solution for every problem.
Yes, indeed. I mean, the universal constructor can build any other type of machine. It basically has to be programmed to do so. And of course, the primary product of the machines are the machines of production themselves, so they can be adapted to build whatever you want. It affects within the bounds of reason, almost without limit. Yes, that's correct.
Is there a midway point you've considered where instead of jumping to a universal solution for everything, what is the most pressing need to solve?
That's a good question, but I mean, the answer is no, and the reason is because I think the cost argument is so important, because every time we launch anything to the moon, it costs money, a lot of money. And yes, you could potentially build things using, some kind of manufacturing capability. But to get the actual exponential growth in productive capacity, you need to build a self-replicator. And that means we have to build this universal construction system. Well, it's not absolutely essential to build a universal construction system. I mean, you could build a self-replicating machine which basically just stamps out something which is completely useless and just replicates. The universal constructor is what makes it useful. Did that answer your question?
Somewhat, yes. However, I still wonder if there's an interim step. So this is you're essentially describing a single step to full solution, and I think that's an artifact of the way you're drawing your box around what a universal constructor machine is. I wonder if there's a way to break the universal constructor machine out to its component machines, and one of them is independently useful as well.
Right. Yeah. I mean, we've already effectively done that. We've demonstrated we can extract aluminium, for example, from sort of lunar regolith simulant. So that in itself is quite useful because you can use aluminium for all kinds of things. So that's a component of the self-replicator, but I think by itself would also be very useful. Does that answer your question?
Absolutely, yeah. It's a fascinating discussion, and I'd happily take up hours more of your time, but no, thank you.
Thank you.
It is interesting. Yeah. Any more questions? Okay. We are a little over time, but I think it was worth it. We could go on for hours, I'm sure. But I just want to thank you, Dr. Ellery, for your presentation and discussion tonight. And no doubt that, I think there'll be more discussion. If anybody does have further questions, please reach out and we can try to pass on your questions.
Sure.
I just want to point out that our next, and by the way, thank you all, everybody for joining us. Our next session will be on March 10th is currently the plan, probably the 10th or 11th. And during that talk, Dr. Shahram Pirzadi is going to present MBSE, using MBSE for managing intellectual property in technology organizations. So a little bit of change in gear in our topic. I hope that you can all join us for that one as well. But we'll close here. I'll stop the recording, and I just want to thank you one more time, Dr. Ellery. This is fascinating. This really is fascinating, and I liked the reference you made to steampunk with the vacuum tubes. You know, isn't that funny? If we rely upon vacuum tubes once again, and maybe only until such time that we can develop the facilities we need to work with silicon up and silicon up on the moon.
Anyway, it's been a blast for me as well. Thank you very much for inviting me. I hope you have enjoyed it. Thank you.
Yes. Take care, everybody.
Okay.
Bye for now.
Bye.